So question 1 was about a boy riding a bicycle over a curb, and I wanted the solution. There were some various values given, but before we do that, let's make some assumptions. Okay, we can assume that the bicycle and the boy fall as a rigid body, so that it's one complete component. We don't need to worry about separate degrees of freedom as part of that entity. Okay, so we can assume the mass, and basically it's just going to be subjected to an initial downward displacement of that 5 centimetres. And so we can represent it by drawing a little diagram. This will help us in solving the problem. There's the curb. So we've got a mass connected to a spring and a damper, and it's moving, and then it comes across this curb, which we've said is 5 centimetres. And it asks, what is the solution? And the question asks for a solution in a specific form. So what I'm going to do is I'm going to solve it a certain way and then convert it, but I'll also talk about another way you could go about solving it. So we know in the vertical direction, if I say that this direction is x, okay, in the vertical direction, what is the initial displacement? Okay. The displacement is obviously going to be 5 centimetres. That's how much it moves. If we say that the thing crosses over this point at time equals 0, okay, it moves down by 5 centimetres. So since x is downwards, we know that x0 is 0.05 metres. Now the velocity at time equals 0 we know is 0 metres per second, okay? Because at this point, when time hits 0, in terms of the downward direction, there is no velocity. It's not moved yet. It's only after time equals 0 does the thing actually move. And so this is how we can set up this equation, and these are our initial conditions. Okay, I see. So the way that I'm going to go and solve it is I'm going to look at my equation sheet, and I see that on my equation sheet, my formula sheet, which you should all have by now, here we go. I've given you this is a formula sheet, okay? You see this formula here, okay? X of t is e. This is quite hard to see. I'll zoom in a bit. This is on your formula sheet, okay? It's now out of focus. Is it going to focus? No. That doesn't help a great deal. Okay. If you've got your formula sheet, you can see it. But basically, I've got a solution here, and that solution is useful because in that solution is the initial conditions already set out. So you've got x0, x dot 0, and various other terms in there. And so that's the solution I'm going to use. So I'm going to write it out. We can write it out big here. I'll zoom in a bit more, get a bit more space. Okay, so the solution, this is, like I said, in your formula sheet, so you don't need to remember it, minus zeta omega naught t x naught cosine omega dt plus x naught dot plus zeta omega naught x naught divided by omega d sine omega dt. And that, like I said, is on your formula sheet. So you don't need to remember that. And we went through the solution to that equation, where that equation comes from. That was back in chapter 2. If you looked at the alternative form section, it's on page 31, the derivation of that question, or that equation. And this is quite useful because we've got the initial conditions. They've been given in the question, so we need basically plug in those numbers, these initial conditions, into this solution, and we'll get a solution. Okay? But there are various things we need to work out before we do that. Obviously, we've got an omega naught in here. We need to work that out. That's relatively straightforward. There's a zeta we need to work out, and there's omega d which we need to work out. So there's three things that we need to satisfy to get the solution to this problem. And so let's do that. So omega naught, we know, is root k upon m. We've been given k, and we've been given m, and we've been given c. M, we know it says the weight is 800 newtons, so obviously we need to divide that by g to get the mass. Okay? And the stiffness has been given to be 50,000 newtons per metre. So we know that this is going to be 50,000 divided by the weight, 800, but obviously that's divided by g to get the mass in kilograms. So this bit is the stiffness, and then 800 divided by 9.81 is the mass. And so you plug in the numbers and you do the calculation, do the sums, you should get something like 24.7614 radians per second. So there's omega naught. We need to find zeta. And again, we can calculate zeta from the damping, the mass, and the stiffness. Okay. Zeta is defined as the damping divided by the critical damping, or the damping constant that will give you critical damping. And we've found out that in the notes in chapter 2 that Cc is 2 root mk. And so it's basically, again, it's just a matter of plugging in the numbers. Damping constant was 1,000 newton seconds per metre. And we have 2 root m, we know is 800 divided by 9.81. And k is 50,000. And if you do those sums, you get a damping ratio of 0.2476. Notice there's no units with the damping ratio because it's simply a ratio of two damping constants. So the units cancel out in a sense. And now we have omega naught and omega and zeta, we can find out omega d. And the equation for omega d, one of the equations, is 1 minus zeta squared. So omega naught times by the square root of 1 minus zeta squared. We've got omega naught, we've got zeta, so we can plug in the numbers. 24.7614 square root of 1 minus 0.2476 squared. After you do the sums here, you get 23.9903 radians per second. So now we have everything to stick into this equation. Okay, we've got omega naught, we have zeta, and we have omega d, the damped frequency. Okay, and we can stick that in obviously in here, omega naught, and omega naught here. Omega d comes into these points, okay, and then zeta obviously is here and here. And for x naught and x dot naught, we have them defined up at the top. And so let's plug in the numbers. xt equals E minus zeta 0.2476, omega naught's 24.7614 times by t, and then all multiplied by x naught, which is 0.05, cosine of omega d, so that's 23.9903 times by t, plus, and then we have a big fraction, 0.2476, 24.7614 times by x naught, which is 0.05, divided by omega d, 23.9903, and that's multiplied by sine not quite fitting on the page. Let's zoom out a tad. There we go. This is zeta, if you can't read it. I'll cross it out. 0.2476. So that's sticking all the numbers in, and then obviously you can do some sums to simplify things down, and I get e to the minus 6.1309 t, 0.05 cosine 23.9903 t plus 0.0128 sine of 23.9903. Okay, so there's the solution. That's the answer. That's the motion of the bicycle and the boy after it goes over that curb. And you can see that it's a sinusoidal motion that decays with time. Free oscillation. Now the thing is that the question asks for the solution to be in a certain form. And the form that it asks for it to be in is x of t equals a cosine, no, I lie, a e to the minus zeta omega 0 t cosine of omega d t plus alpha. It asks for it in that form. And so we need to convert this equation into this equation. Now back in chapter 2, when we talked about the different responses and different forms of responses, there were some equations that I gave where you can convert that into that and backwards and the other way, okay? And what I said is that A is the square root of A1 squared plus A2 squared, and alpha was the inverse tangent of A minus A2 over A1. And you'll find those equations, they're not on the formula sheet, but they are on page 30 in your notes. Okay? Where the amplitude in this second equation is basically the hypotenuse of those two amplitudes. So that's using Pythagoras' theorem, okay, and the angle tangent is minus A2 over A1. And so we can find out what A is. A is the square root of 0.05 squared plus 0.0128 squared. And if you do those sums, you get 0.05161 meters, and so we get A to be 0.50161, okay, and alpha, which is the angle, the phase angle, is minus 0.2502 radians. And so we plug those numbers into this solution and we get x of t equals A 0.05161 e to the minus, and that's the same as what's up here, 6.1309 t cosine omega d, well, that's the same up here, 23.9903 t, oops, minus 0.2502. This is t, obviously. So that's question 1. That gives you the solution to question 1. And that's one way of solving it. There is an alternative way to solve it, okay, and that is simply to take this equation, this one up here, and then apply the initial conditions. We know that at time equals 0, we know x of 0, because that's been given, and then what you do is you take that equation, you differentiate it with respect to time, and then you have an equation for velocity. And so we know the initial conditions when velocity is 0. And so you can therefore then apply those initial conditions to that equation and you'll get the same answer, okay? It doesn't make any difference. You'll get exactly the same response if you do it in that form. So we have this equation, A e to the minus zeta omega naught t cosine omega d plus alpha. And so x of naught is going to be A e to the power of, obviously there's a t with the exponential, okay? E to the power of 0 is 1, so that disappears. And then obviously cosine, this is omega d times by t. Well, that's going to be, that term is therefore 0, so it's simply A cosine alpha. Okay, so there's one equation, two unknowns. Then you find x dot of t. Okay? So A is a constant, so that just remains, and then we have, this isn't given on the equation sheet, so you have to work it out, but you end up with A e to the minus zeta omega naught. This is where learning your differentiation rules really helps. Minus omega d sine omega d t plus alpha. And so x dot you set that equation to 0 when t is 0, so that term turns into 1. We end up with cosine alpha and sine of alpha. Well, you know that a cosine alpha is that, okay, is x naught, so you can replace that. You could therefore find out what what alpha and a are determined, because you have two equations and two unknowns, okay. I won't go through the motions, but you can do so in your own time. So even if you didn't spot the equation that we used, the one where the applied, this one up here, if you didn't spot this equation in this formula sheet, you can still solve it from the answer that I've given you, which is this equation here, this one. Okay, just by applying the initial conditions. So that's question 1.